Hey guys, welcome to our lesson video for section 8.3. 8.3 is going to be focused entirely on a letter. And specifically, we're going to be focusing on the letter E, which as you may know is also a mathematical number as well. And we're going to we're going to use E to look at compound interest in the continuous form. And then we're also going to derive where E comes from as well. So for today's lesson, you're going to need a note sheet that you can set up. And it might be a good idea to use graph paper because there will be a little bit of graphing. But you're also going to need the handout for 8.3 that you'll find on Google Classroom. So please make sure you print out that handout as well before you watch the rest of this video, because I'll be asking you to fill that out as well as part of our compound interest aspects. So when you have both of those things ready, then resume the video. All right, so we're going to talk about the number E. And you know, you guys have been very exposed to a different famous irrational number, pi, and you know that it has infinite digits that never repeat. Today we're going to be looking at another famous irrational number, which is the letter E. And that number also goes on forever without repeating. Starts with 2.718 and goes on from there. I think just like most of you know that pi is 3.14, you should at least know that E is 2.72 if nothing else. E shows up all over the place though. Both in finance and in the natural world, which is why it's such an important number and one that we're going to study in more detail. So we're going to start out today by looking at it in the context of compound interest. So this is where you'll need that handout that I mentioned at the beginning of the video, because we're going to look at how we can explore compound interest all the way to looking at continuously compounding interest, which is actually what most banks do. And we're going to see if we can figure out where the number E comes from, and then actually use that to do a more formal derivation of E. And in the process, we can also figure out the formula for compound interest as well. So what I want you to imagine for a sec is that we take out a special kind of loan. And for this loan, we are going to start with just $1. We're going to use an interest rate of 100%. And we're going to calculate each of these things for 1 year. And our goal is to figure out what the value, how much money we would have in each situation. And as a reminder, our formula here is A equals P, the principal, times 1 plus R over N raised to the NT. So I'll do the first example, and then I'm going to ask you to fill out the rest on your own before you resume the video. So if we were compounding annually, we would be compounding once per year. So our formula would be our amount equals our principal of $1 times 1 plus our 100% interest rate, which is 1, over the number of times we would compound, which is also 1. And we'd be raising that to the NT, which in this case would just be 1 times 1. So if you were to simplify this or put it into your calculator, your ending amount would be $2. So I want you to go through and see if you can figure out the rest of this. Biannually, we would be compounding twice. Quarterly would be 4 times. Every other month would be 6 times. Monthly would be 12 times. Daily, we would be compounding 365 times a year. Hourly would be 8,760 times a year. Every minute would be 525,600 times per year. And then continuously, we're going to look at that one together. So you can skip that bottom row for the moment. But I'd like you to see if you can take a few minutes to use, and obviously using your calculator, see if you can fill out the rest of this table and then resume the video when you've done that. All right, right, so hopefully you filled out the entire table at this point. I'm going to put in some of the values as well. So we would have $2.25, and then we'd have $2.44, and then $2.52, $2.61. And you can kind of get a sense here of where we're trending. 2.71, and then we'd have $2.72, and again here $2.72, and we're getting closer and closer to that E value. So now if we compounded continuously, that would be essentially like we'd be putting in infinity for our N value. So we would have basically our amount would be 1 times 1 plus 1 over infinity raised to the infinity times 1. And you can kind of get the sense here, right, that as we're moving along, every time our number of compounds increased, we got closer and closer to 2.72 or 2.718. In other words, we got closer and closer to that value I showed you for E. So we have 2.718, 28182. Basically, as we get closer and closer to continuously compounded interest, we're also getting closer to the letter E. And in fact, this is something that you're going to look at more in pre-calculus as well, but the definition of E is actually the limit as some variable x approaches infinity of the formula 1 plus 1 over x raised to the x. And you can see that here, that is exactly the same as what happens when we compound continuously when we have a $1 loan at 100% interest rate for 1 year. So the purpose of this handout in this example was to show you that you can actually get to E simply using compound interest, which is why I mentioned earlier that it shows up in a lot of financial applications. So let's see if we can go the other way with this as well. Let's see if we can actually derive the formula for continuously compounded interest, because that is really what banks frequently use in order to calculate how much money is owed on a loan. So imagine for a sec that we start with our typical compound interest formula. So our amount equals our principal times 1 plus r over n raised to the nt. And we're going to do just a few manipulations here with our goal being to get to a situation like what we just saw on the last screen. And the first thing that we're going to do is we're going to substitute in, we're going to put in r over r in the exponent, and you'll see why in a moment. So let's say we had r over n times rnt over r. So now what we're going to do is we can actually then rewrite this as, we can rewrite this as p times 1 plus r over n raised to the n over r, which is then being raised to the rt. So all I'm doing here is I'm just splitting this up and moving this piece of it into its own power. So just using the power to the power rule backwards. Next, what we're going to do is rewrite this middle piece just a little bit here. So we have p times 1 plus, instead of r over n, I'm going to write this as 1 over n over r, which again is mathematically equivalent. But the reason we're doing that is because we wanted to get in a situation where we have those two n over r terms. Because now, if you think about it, if we were to make our n approach infinity, these two n over r terms, right here and right here, would both approach infinity. So in other words, we would approach infinity here, and we'd also approach infinity here. And if you look at this, if we go back a screen for a second and look at the definition of e is the limit as x approaches infinity of 1 plus 1 over x raised to the x. So what I want you to notice here is that's the exact same thing as what we have right here. If we imagine that n over r is our x value, then we have 1 plus 1 over x raised to the x. And if we take that and make n approach infinity, in other words, we're compounding continuously, because remember that n is the number of times we're compounding per year, everything that's in that red box right now is just the equivalent of e. So in other words, we would have our amount equals p times e raised to the rt. And a lot of times you'll hear people talk about this as the PERT formula, because it's just pe to the rt. So you can see here that it's actually fairly straightforward to derive the formula for continuously compounded interest, p to the e to the rt, as long as you understand a little bit about how limits work. And we saw that based on that handout we looked at in the last slide. So this is just one application of e. There's actually lots more applications of e throughout real life. And it shows up all over the place in different areas of science, as well as finance as well. And you can see that here. I mean, everything, E is in formulas everywhere from radioactive decay to medicine to physics to electrical engineering. Obviously, it's in finance, as we just saw. So this number E shows up throughout applications that you're going to see as you move forward in all these different fields. So let's look just a little bit at how E would show up in different situations like we've looked at before. So for example, if we wanted to sketch a graph of y equals 2 times e raised to the x minus 4 plus 3, we can do that pretty easily, because we would think about, just like before, 2 would be our y-intercept, but we would be shifting it to the right 4 units, as well as up 3 units. So in this case, I would go right 4, up 3, erase my old one. I would also take the asymptote up 3 as well. And then the key here is that the number e is obviously, it's greater than 1. So in this case, our multiplier is greater than 1, which tells us that our curve is going to start along the horizontal asymptote and curve upwards. So you can sketch graphs with e in them just by remembering that e is really just any other multiplier, it's greater than 1. Similarly, we can also simplify expressions with e as well. For example, if I have the cube root of 64 e to the 9x plus a square root of 81 e to the 6x, well, that's just the same thing as the cube root of 64 is 4. And I would have, if I turn this into a fractional exponent, I would have e to the 9x over 3. And I could add that, so the square root of 81 is 9. And then we would have e to the 6x over 2. And we can simplify that to, since 9 over 3 is just 3, we have 4e to the 3x plus 9e to the 3x, which simplifies to just 13e to the 3x. So we can simplify, think of e as a base that's common to e, just like any other two common bases. Also, we can think about whether something with e in it represents exponential growth or decay. So for example, if we had e to the x, that would obviously be exponential growth because e is greater than 1. If I have e to the negative 8x, I could think about rewriting that as e to the negative 8th to the x, which is the same thing as 1 over e to the 8th to the x. Now 1 over e to the 8th is going to be an extremely tiny number because e to the 8th is going to be a very large number. So 1 over to e to the 8th would tell us that this formula would represent exponential decay because our multiplier would be very, very small, much, much less than 1. So this situation would be an exponential decay situation. So the key here is I wanted you to see where E comes from. And I also wanted you to understand the connection between E and continuously compounded interest. And then you can see from the end of this video that E can be manipulated and graphed just like any other multiplier in an exponential function. So give the homework a try and let me know if you have questions as you're working on it.